Okay. So, okay, yeah. Okay, so welcome again. So we are in the last talk of this semester as well as last talk of this series by Sergio. So he will talk on low degree cohomology, extension spaces and boundaries at infinity, and maybe discuss some open problems related to that. Yeah, so over to you, Sergio.
Thanks a lot for the introduction. I want to focus on the comparison between the bornological cohomology we were looking at last time and the coarse cohomology we introduced earlier. So let me start with some reminder. So what did we see at the last part of the last talk? Basically, we introduced this category of topological bornological spaces. So the objects here are we have a set, a topology, so topological space, and some bornology, so a set of bounded sets, which is compatible with the topology, in the sense that every bounded set is contained in an open bounded set and in a closed bounded set. So that's our objects. And let me remind that a morphism in this category is a continuous map that is also proper. So the preimage of a bounded set has to be bounded. We had also introduced the bornological cochains. So what was that? Basically, to every topological bornological space, we had associated a cochain complex. And yeah, so the cochain complex in degree n, this is the group of n cochains that are boundedly supported. So the intersection of the diagonal and the closure of the support has to be bounded. And then this is contravariant. So yeah, every continuous proper map induces a cochain map. And then we get a cohomology functor. So this is bornological cohomology. Now, the idea is to use this functor to compute coarse-cohomology. How can we do that? So first of all, I'd like to be able to compute this in an easier way. And there is this theorem. Okay, theorem from last year. Was it? No, it was the beginning. It was the beginning of this year, yes. And basically, it says that this functor is naturally isomorphic to a colimit of cohomologies at infinity. So for any topological bornological space, the bornological cohomology, let's say with coefficients in G, is naturally isomorphic to the colimit of the Alexander-Spanier cohomology at infinity. Okay. So this is reduced Alexander-Spanier cohomology shifted in degree, and we take the colimit by removing larger and larger bounded sets. This makes it easier to compute this cohomology. So let's see some examples. First of all, some examples. Remember that in this category, the space of natural numbers is isomorphic to the space of integers. Right, and so if I want to remove larger and larger bounded sets, I'm just removing larger and larger finite subsets. And since the topology is discrete, I will basically get that the bounded cohomology. So let's think if the degree -1 is positive, I'm going to get 0. So this is going to be 0 for degree at least 2, because the space is discrete. And if not, I will just get a colimit of fewer and fewer points. Okay, so in general, I get 0, but also in degree 0, yes, and degree 1. Yeah, the cohomology is 0 in the end. So the cohomology is 0. So I don't see anything here. Okay, the cohomology doesn't see anything. More examples. What if instead of the natural numbers, I consider now the infinite ray? Well, now let's compute it. I can choose a cofinal family of bounded sets. So for each n, we'll consider the bounded set 0n. So this is a cofinal sequence of bounded sets in the sense that it is increasing and every other bounded set is contained in one of those. This means that I can compute, because of the theorem, I can compute the coarse-cohomology as a colimit in n, so let n go to infinity, of the reduced Alexander-Spanier cohomology of the complement, but the complement is n infinity. So now this is just homotopic to a point, and all of the inclusions between these spaces are homotopy equivalences. So in the end, this is just the cohomology of a point, which is 0, because it's reduced. Okay, so this is the reduced cohomology of a point. So it's 0. More examples, maybe a more interesting one. Let's look at Euclidean n space in general. So in this case, we also find a cofinal sequence of bounded sets which are balls around the origin of radius n. So when I use the theorem, I see that the bornological cohomology is naturally isomorphic to the colimit of the Alexander-Spanier cohomology of the complements. So this is the complement of a ball. Well, if this was the plane, let's imagine this is the plane, and I just take a ball out. So I'm looking at this region over here. You can clearly see that this is homotopy equivalent to a circle. Okay, I can contract this to a circle or retract this onto a circle. So this space here is homotopy equivalent to an n-1 dimensional sphere. And all of these inclusions between complements of balls are homotopy equivalences. So this is just the reduced cohomology shifted in degree of the n-1 sphere. Okay, so we get G in degree n and 0 otherwise. Okay, so something we're seeing already is because this bornological cohomology is a functor, we see that if Rn is, we didn't need to use it, but yeah, Rn and Rn, if they're isomorphic in this category, then they have the same cohomology, and so they have to be of the same dimension. Okay, they have to be of the same dimension. All right, so here are some examples. Now, how can we relate this to coarse-cohomology? Before we move on with that, is there any question about this part?
No.
Okay. Perfect. So, coarse versus bornological cohomology, these two theories are related, and that's what we want to exploit. So let's focus on the case of a metric space. So now we assume that we start with a metric space. I can regard it as a coarse space. Then it is a coarse space with the metric structure, but it is also a topological bornological space with the induced topology and the usual family of bounded sets. So because it is a coarse space, it has a coarse cohomology. And because of this, it also has a bornological cohomology. I want to share the general picture with you. So now, what do we have? We have our basic cochains. Okay, inside, we have the bornological cochains. We also have the locally zero cochains. Right? And if I take the cokernel of this inclusion, then this is the Alexander-Spanier cochain complex. This gives the Alexander-Spanier cohomology of X. Now, if we have time, we can see why, but for now, you can believe that the cochain complex, the coarse cochains are included in the bornological cochains. So if a cochain is coarse, it is also bornological. So now I want to say that this gives the Alexander-Spanier cohomology. This cochain complex gives the Alexander-Spanier cohomology of X. This gives, remember, this gives 0, except in degree 0. This gives the bornological cohomology. This gives the coarse cohomology. And this complex here would just be, the cohomology it would be almost the same as this one, but shifted in degree and reduced. Okay. So now I want to focus on this inclusion here. So in general, no matter how crazy my space is, because we have this inclusion, of cochain complexes, we also have an induced map in cohomology. There is an induced map from coarse-cohomology to bornological cohomology. When is this map an isomorphism? That's something I would like to know. When is it an isomorphism? Okay, so we already know some examples where it isn't. So we already know that in general it's not going to be. Well, actually, yeah. So we have to be careful here because, for example, the natural numbers and the infinite ray, they are coarsely equivalent as coarse spaces. However, they are not equivalent as topological bornological spaces. So we have to be careful here because if I look here, then this cannot be distinguished from the integers. But the integers are not related to the natural numbers in this other category. So why is this happening? It's because the failure of this map to be an isomorphism is measured in the cohomological information that bounded sets carry to infinity. So if the bounded sets do not carry cohomology forever, then this map is going to be an isomorphism. So let's try to formalize this idea. Okay, so again, the idea is that no cohomological information is carried along bounded sets to infinity. So I need some definition here. We'll say that X is uniformly contractible at infinity if there is no information in bounded sets that gets carried to infinity. So if, now this is a bit technical, there are two control functions and a base point. The choice of the base point is not important here. Such that if we have a bounded set B, and let's say that the diameter of B is R, when this bounded set is far away from the base point, so if it is far away from the base point and this is controlled by these functions, then eventually all the non-trivial information that B carries dies at some bigger bounded set. Okay, so what do I mean by that? Let me go back a moment. Let's look at this limit. We have this theorem right here. So what I mean is, if there is non-trivial topology in a bounded set V, I want a bigger bounded set that kills this information. So inside a bigger bounded set, this information disappears. Then it will not be affecting this colimit. So that's something we can write like this. So whenever my bounded set is far away from the base point, there exists a bigger bounded set in which this is contractible. So B is contractible inside a set of diameter rho of R. So this means that there is some B prime bounded of diameter rho of R such that this inclusion is null homotopic. This inclusion is homotopic to a constant map. Okay, so this is uniform contractibility. Let's see. Now, how can we use this? And here's one of the main theorems. This was proven by Banerjee in 2024, in January of 2024, and it goes as follows. If X is uniformly bounded, uniformly contractible at infinity, then this map from coarse-cohomology to bornological cohomology is an isomorphism. So, okay. So before we saw an example, before we also had a theorem on how to compute this bornological cohomology. So we can now put the two of them together and say that as a consequence, for this uniformly contractible at infinity spaces, the coarse cohomology can be computed as the colimit of Alexander-Spanier cohomology at infinity. So at infinity, I mean by removing larger and larger bounded sets. Okay, so also another way to compute this is taking balls. So if P is a base point, and if P is a base point, then the coarse cohomology can be computed as a colimit of the cohomology of complements of balls. This is what we did earlier. So now we can compute coarse cohomology of many spaces thanks to this. So some examples. This space Rn is uniformly contractible at infinity. So this coarse cohomology is isomorphic to the bornological cohomology. So the coarse cohomology of Rn is isomorphic to the bornological cohomology. And we had already computed this by taking complements of bigger and bigger balls. This is the coefficient group in degree n, 0 otherwise. So coarse cohomology is detecting the dimension of the space. Okay. This theorem can also be used to compute the coarse cohomology of spaces that do not satisfy the hypothesis, because I can replace spaces by coarsely equivalent ones. So here's an example. Set n is not uniformly contractible at infinity. If you give me a bounded set with at least 2 points, there is no way to embed it into a bigger bounded set in which it is contractible. So this is not uniformly contractible at infinity. And again, let me repeat why. So imagine set square as a grid. So if the space was uniformly contractible, every bounded set should be contractible inside of a bigger one. So let's say that I take these 3 points here. So this is a bounded set. There should be a bigger one in which this is contractible, but this space is discrete. I cannot move freely to contract this point into a single one. Okay, so, but this means that in theory, I could not apply this theorem directly to the space. However, I can try to find a space. I can try to find a space that is coarsely equivalent and that does satisfy this theorem. So this is coarsely equivalent to Rn, and so because of the theorem, we can also compute the coarse-cohomology of set n. Okay. So some curiosity here. This is also a way of saying that if you have set n, yeah, so if set n is coarsely equivalent to set m, then the coarse-cohomologies have to be isomorphic, and because of our computations, then the dimensions have to be equal. Okay, so the dimension of set n is a coarse invariant, and I can say more. So let's think of the classification of abelian finitely generated groups. This is all part of the same example. So if A is abelian and finitely generated, then we know that it has some free part, free of torsion, and some torsion subgroup. So actually, for these abelian finitely generated groups, we know that this torsion part is finite. T is finite. So in geometric group theory, as groups, A is coarsely equivalent to set R. So this means that this gives a corollary. So another corollary or consequence is if two abelian groups, A1, A2, are finitely generated abelian finitely generated groups, then they're coarsely equivalent if and only if they have the same rank. Okay? Because yeah, this is coarsely equivalent to set n when where n is the rank. This is coarsely equivalent to set m where m is the rank. And then these two are coarsely equivalent, which by our previous computation implies that the ranks are the same. Okay. Okay. Just as a curiosity, there is another way to compute this using growth, polynomial growth. Okay, so if some of you are interested in geometric group theory, you might know about the growth of a finite generated groups. And that's also a coarse invariant that you can use to prove this kind of results. Okay, so you can either use coarse-cohomology or growth types. Okay, so that was some examples. What happens with the natural numbers again? So again, natural numbers, they're coarsely equivalent to the infinite ray. And so the coarse-cohomology is the same, they're isomorphic. Okay, so again, this space does not satisfy the conditions of the theorem, right? Because this goes to infinity. So let's say we have a point here, another here, here, here. If I choose any bounded set with at least 2 points, then I cannot embed it in a bigger bounded set where it is contractible. Okay, so the natural numbers, they do not satisfy the theorem. However, again, we can replace it by another space which does satisfy it, and that's the infinite ray. So because this one is uniformly contractible at infinity, then I can apply the theorem. So because of the theorem, let me compute it in the next page. So because of the theorem, the coarse-cohomology of the infinite ray is the colimit of the Alexander-Spanier reduced and shifted cohomology of complements of bounded sets. But remember that I can instead take complements of balls around a fixed point. So for convenience, I will choose balls of radius n around the origin, and then I will let n go to infinity. So we had computed this earlier. It was the reduced cohomology of a point, which is 0. Okay? Okay, so now we have some examples. Okay, so far, any questions, any curiosity? Okay, so this is the main idea that I want you to keep, that for nice enough spaces, the coarse-cohomology can be seen as some colimit or limit of the usual cohomology of neighborhoods of infinity. Okay, this idea of taking away, stripping away larger and larger bounded sets is just getting close to infinity, getting closer and closer to infinity. Okay. So if there are no questions, I'd like to talk a bit about some problems. First of all, the Mayer-Vietoris sequence. So there was a question regarding this Mayer-Vietoris sequence in coarse-cohomology last time, and I didn't find it in cohomology, but I found something interesting for homology. Okay, so just for your curiosity, there is some dual notion. There is some dual notion of cohomology which is just coarse homology for coarse spaces. And there is indeed a Mayer-Vietory sequence for that. So the main problem of Mayer-Vietory sequence is if you write your space as an union of two subspaces, when does it make sense to say that this pair is an excessive pair? Okay, so we have this diamond diagram here. For topological spaces, the pair was an excessive pair if this condition was met. So X is the union of the interiors. What should happen here? So there is a nice article by Mitchener called the Mitchener. Let me check the name just in case. Coarse homology theories. Coarse homology theories. And so something interesting he's doing there is he replicates the ideas from Eilenberg-Steenrod axioms that we already know for usual homology theories, but for the coarse environments, so for coarse spaces, for homology theories of coarse spaces. So one of these axioms has to do with the Mayer-Vietory sequence, and he found a condition that actually makes a lot of sense. The pair AV to subspaces, then we say that AV is an excessive pair if for every entourage there exists another entourage such that the intersection of the thicknings is contained in the thickening of the intersection. So this is a way of saying that from far away, the intersection of A and B still looks like the intersection of A and B. It still looks like it. It makes a lot of sense. I'm saying that for any thickening of A and B, if I consider the intersection of these thickenings, then it will be contained in a big enough thickening of the intersection. So whenever this condition is met, there is a Mayer-Vietory sequence for homology theory. I would like to know, so this is only a partial answer because I still am not sure how it works for cohomology. Okay, so this is homology. But I'm guessing that there should be a reasonable way to also do it for cohomology. It should be dual to this approach. Okay. So this was one question from last week. Okay, and also I said I was going to talk a bit about products. So not much, but just a curiosity I want to share with you. So you remember that if we have a coarse space, we had defined the coarse cochain complex as a and well, let me be more explicit. I want to define a product in coarse-cohomology. For that, I will take the coefficient group to be a ring. Okay, so right now I will take coarse-cohomology with coefficients in a ring. So now I can define a multiplication. How do we do that? So first of all, the coarse-cochain complex with coefficients in R is, as always, a subcochain complex of the basic cochains. So these basic cochains, they have a cup product on it. Okay, so there is a nice way to define a cup product. If I take an n cochain and an m cochain, I can define an m plus 1, m plus m cochain. Okay. So, whenever you have two cochains, the cup product is well defined, and since x0, xm plus m, so basically you want to multiply the value of phi on the first n simplex, and then you chain this together using xn, and you apply c. So this is the cup product. And some nice properties, it endows this cochain complex with the structure of a differential graded algebra. Okay, so one first idea that could cross our minds is, let's try to, okay, we have this product structure here, let's try to restrict it to our coarse-cochain complex. Sounds reasonable, right? So we would like to try something like this, right? So if I and indeed it is true, if phi is a coarse-cochain and C is a coarse-cochain, then the cup product between them is also a coarse-cochain, which means that now this coarse-cochain complex also has a multiplicative structure. Okay? And so, because this is a differential graded algebra, now this induces a multiplicative structure on cohomology. So this is now a graded cohomology algebra. I can talk about the multiplication of cohomology classes. Why don't we do that? We don't want to do this. Why? Well, it turns out that this product here is 0. So unfortunately, this doesn't work because, or it is not interesting to consider because the product is always identically 0 in cohomology. Why is that? Well, because this product is trivial because actually this is an ideal. The coarse-cochain complex is an ideal of the basic cochain complex. What I mean by that is that if phi is a coarse cochain and C is any cochain, then the product is always going to be coarse. And also in the other side. So it's a two-sided ideal. And then the product has to be zero. Why is that? Well, because, yeah, okay, I can, whenever I multiply two elements in the coarse-cochain complex, so I'm defining a linear map, right? Or a multiplication here. So one thing I can do is, okay, let's regard the first component as a coarse-cochain complex, as a coarse cochain, and the second component just as a cochain. There's an inclusion here. Okay, we can also do it with the other component, and then we can take the multiplication. This diagram is well defined because the coarse cochain complex is an ideal, and basically this is measuring the reason why the product vanishes in cohomology. So there are two reasons why. This reason and also this reason, the product is vanishing in cohomology. So this is starting to look very similar to Massey products. You know about Massey or higher products in cohomology. When the product between two cohomology classes vanishes, there is a triple product defined. So that's something we can do in coarse cohomology, and it turns out to be very interesting. You remember that if we choose a base point, so let B be a base point, we had defined a contraction of the basic cochain complex, right? So again, if phi is an n+1 cochain, then the contraction sends x0, xn minus 1 to phi of b, x0, xn minus 1. So this map was important some sessions ago because it's a contraction of the basic cochain complex. But now we can use it in a different way. So there is something called the row product. So the row product is a multiplication, some operation defined as follows. So the row product of two coarse cochains is, I will first consider the contraction of phi. Sorry, this is a bit confusing with the degrees. Let me be more specific. So I will take a K cochain and L cochain, and the result will be a cochain. So first I will contract phi. This has now degree K minus 1. Then I multiply with psi. This has degree L. Then up to some adjustment in the signature, I will first multiply with phi and then the contraction of psi. So this has degree K, this has degree L plus 1. So what am I doing here? I'm basically adding together the two reasons why the cup product vanishes in cohomology. Okay, so this corresponds to this part here, and this corresponds to this part here. I'm adding together these two reasons. the result is then a cochain of degree k plus L minus 1. So, okay, this is not exactly a differential graded algebra because of this shifting in the degree. Okay, it's not a k plus L form, but it is still an interesting multiplicative structure. And turns out that it descends into a product in cohomology. So I can consider a coarse-cohomology class, an L cohomology class, and this yields a coarse-cohomology class in degree k plus L minus 1. So this is called the row product. Row product. And turns out that this product is, so it all depends on the choice of a base point. You see here, we chose a base point, and when we did all of these definitions, so it turns out that this structure does not depend on the choice of the base point. In cohomology. Does not depend on the choice of base point. 4 degrees, at least 2. Okay, so in degree 0 and 1 has to be careful, but other than that, the product is not dependent on the base point. So it's really something intrinsic of the coarse cohomology. And now this product is not vanishing. This product is now very interesting. In general, it will not vanish. How do we know that? Well, also another theorem. You remember this computation coarse cohomology here? Turns out that theorem here, theorem, and I will finish with this. Time for questions. Okay. This was from the beginning this year as well. Magnetic space. That goes for homology, bornological homology. About listing of features.
Sergio, your voice got very lower.
Since a long time ago or just now?
No, just now.
Oh, okay. So then I will repeat from
Now
here.
it's good. The voice is good now.
Okay. Thanks for telling me. Interrupt me again, please, if it happens. So, so I will repeat from here, from the beginning of this year. If a theorem, if X is a metric space, remember that we had this morphism of also a coefficient ring. Remember that for the product to make sense, the coefficient group actually needs to be a ring. Okay, then this is a morphism of algebras. And in particular, we have a way of computing the row product. So corollary, computation, we can compute computation of the row product. So if X is uniformly contractible at infinity, as before, then the map, this isomorphism from coarse-cohomology with the raw product. Sorry about the notation. This is very unfortunate. This star here is the degree. Maybe I use a point now. This is the degree and this is the raw product. Okay. So this isomorphism that we had from the colimit, from the coarse-cohomology to the colimit of Alexander-Spanier cohomology infinity is actually also an isomorphism of algebras. So, or almost that. Okay, so now we have a cup product here. This is a colimit of usual cohomology. So here we do have a cup product. So it's also almost an isomorphism. Why do I say almost? Because there is some adjustment in the degree. So the product of two elements here gets sent. So if this is, let's say this is F. So the isomorphism satisfies the following. F of the product is F of alpha times F of alpha times F of beta, but it's not exactly that. There is some sign here. Okay, so it's plus minus the product. So up to some adjustment in the sign, this becomes an isomorphism of algebras. And this makes it easier to compute this raw product now, because we can use the usual cup product in cohomology. And in particular, we see that this cup product is non-vanishing. It actually carries some information. Okay. And I think it's now time. I like to stop here so that there is also time for questions. And I also would like to appreciate all the attention and that you're also here to listen to these talks and for your questions. Thanks a lot.
Thanks, Sergio. It's really nice seeing your talk. Uh,
Thanks to all of you. It was a pleasure.
Yeah, thanks. It was a nice series.
Thanks a lot. I'm very happy to do it, to be here.
Yeah. And it's good now you like the one that you described, the Meyer Vittori, that was also so, kind of an answer to the last question that I asked.
Yes. It was a good question. It made me do some research. Yes. I think this is a very interesting article. I like this axiomatic approach to homology theories.
yeah. So, like for the cohomology also, like for this coarse-cohomology or this what is the bornological cohomology? So, both are like, are they cohomology theory?
Can you be closer to the microphone? Sorry.
Yeah. So, I'm saying, are those theories like whatever cohomology you defined here, like coarse cohomology or the bornological cohomology, are those like cohomology theories?
They are in this other sense. So,
like there is this Brown representability theorem says that if those are cohomology theories, then you get a sequence of space so that you can write the homologies as the homotopy class of maps from your space to the those space.
exactly. So these are related but different things. So here, you know this historical paper by Allenberg-Steenrod where there is a list of actions For homology theories,
Yeah,
there is the
exactly.
dimension axiom, there is the homotopy invariance axiom, exactness, Mayer-Vittori sequences. So there is a list of axioms, and if a homology theory satisfies this, then yeah, it's determined by the value at a point for CV complexes. So that's kind of a big result there. So basically, Michener here is doing that, but adapted to coarse spaces. So it's not a homology theory in the homotopical sense, or in the topological sense, as always. It's something analogous for this other world. So when you talk about a coarse, when you talk about a homology theory, you get a sequence of, sorry. So if you talk about a homology theory, you would consider a sequence of functors from topological spaces to abelian groups, right?
Right.
Maybe even taking negative values if it is a generalized one. So if it is a generalized homology theory, it can also take values in negative integers. Here, so this has a list of axioms. Now this is something different. It's not the same kind of thing, but something analogous. So it's not a cohomology theory in the usual sense, but an adaptation, if it makes sense. So, and now for the other part of the question, that's very interesting thing. We know that for homology and cohomology theories, they can be represented by a spectrum, right? So there is this Brown representability theorem between, for example, homology theories. Let's write it like this: homology theories up to isomorphism and spectra up to equivalence, right? And okay, that works for topological spaces, or maybe I can restrict my attention to CV complexes. Question is there an analog of the Brown representability theorem for coarse homology theories? So that's the question, right?
Yes, right.
Coarse homology theories up to natural isomorphism. And so what should a coarse spectra be? Coarse spectra. That is not clear to me. There is some work in this direction already, and it's a nice book by Ulrich Bunke and Alexander, I think it's Alexander Engel. It's homotopy theory of, let me see, homotopy theory. With bornological, let me check, I think it's bornological coarse spaces. So it's Bunke, bornological spaces. Yes, homotopy theory with bornological coarse spaces, exactly. So he has an approach, they have an approach in this book where they consider spectra using infinity categories. So they have an approach, spectra or coarse spectra using infinity categories. So yes, this is something that we are trying to understand better, and there is already a very nice proposal in this book. Yes,
Uh-huh. Right.
it's a very interesting question.
So another one I just wondering if maybe the completely irrelevant. Like you said about the like bornological homology and like this Alexander-Spanier homology, they are related by this co-limit thing, like kind of
Mhm.
away from this bounded set kind of, yeah. So like are there something relevant to like this chain cohomology something?
Is there something similar to homology?
For
Sorry.
the cohomology. Like, are there any map or some isomorphism may be possible for this check homology thing? Like this co-limit
Ah,
thing is a bit relevant, like related to that, I guess. I don't know exactly. I don't know exactly the context, but suddenly when you wrote like co-limit, I feel maybe there may be some connection or something.
so sorry to repeat the question. I want to make sure I understood well. So the question
Uh-huh.
is there a similar result, but for K, K homology instead of coarse-cohomology or
No,
coarse?
no, no. I was saying for the like check cohomology, there is check cohomology for if you like if you have a topological space, then related to for a given open cover of that, like you can define an chain complex, like chain cochain complex, and then define cohomology there. Like
Mhm.
maybe it's not relevant here, but suddenly I just feel maybe there might some connection. It's fine, maybe it's
I
not relevant
think
here.
I think there is. Me, I am not an expert in that, but I think I read something around the literature.
Uh-huh. Okay, okay.
I don't remember if it was in this same book, though. But yeah, there is a way. So there is a general procedure. To, so you have a locally finite. So whenever you have a locally finite uh, cohomology theory for coarse spaces, whenever you have a locally finite cohomology theory for spaces, there is some way um, there is a way to take some limit process of which I do not remember all the details and then define an associated um, coarse cohomology theory. And I don't remember now very sure if K cohomology was also an instant of this. I don't remember if K cohomology was also constructed in this way. If it was, then there would be an affirmative answer to your question.
Okay, okay.
But I should check,
Yeah.
yes.
Yeah, yeah. I'll also look into it. Yeah.
Right.
Yeah. Thanks. I don't have any further question. Yeah. Thank you.
Okay, thank you.
Okay. In that case, we can. Thanks to Sergio, and then we can meet, I guess, next month.
Yeah.
Okay, then bye, Sergio. We'll
Okay,
meet.
Yeah.
it was
Bye.
very nice. Thanks for giving me the opportunity to share this with all of you.
Yeah,
It was
yeah.
a good time.
Yeah. Nice traveling.
Thanks.
Okay, so have a nice vacation and the rest of the month.
Yeah.
Yeah.
Okay.
Okay. See you at some point of time.
Pleasure.
Okay.
Yeah. Yeah.